Although small in land surface area, the country of Costa Rica experiences a variety of rainfall generating power processes and patterns. This complexity arises from the interaction between the two major ocean basins that lie either side of it, the Caribbean and Atlantic to the north and east, and the Pacific to the south and west. The winds associated with the major pressure belts of the world, the continental masses of North America and South America, and how all of these interact on a seasonal basis with the complex topography of the region. Before we start in on the climatology, it's important to at least get a brief understanding of two drivers of important climatological questions. The first one is, what drives winds and the directions that they flow in? And the second one is, what is it that makes it rain? Air always wants to move from zones of high atmospheric pressure towards zones of low atmospheric pressure. In the diagram on the right, these is indicated here as the zones or the lines in light green of the intended path. Due to the rotation of the Earth, winds appear to be deflected to the right of their intended path in the northern hemisphere. So in the upper portion of the diagram, the winds intend to move up the diagram, but are forced to make a right-hand turn, producing the diagonal winds indicated there as the apparent path. In the lower half of the diagram, the winds are moving from high to low, moving down the page. In this case, the winds are determined to make a right-hand turn just as one might make a right-hand turn in a car, which makes them veer off in the direction indicated, even though visually this appears to be the left. The same principle applies in the southern hemisphere. Winds always want to blow from zones of high atmospheric pressure to low atmospheric pressure, but in the case of the southern hemisphere, the winds are deflected to the left of their intended path, giving the apparent paths indicated here in the heavy green. The second question, what makes it rain, is controlled by a very simple fact, which is that hot air can hold more moisture than cold air. This diagram, even though it looks a little complex, shows on the horizontal axis some measure of temperature, degrees Celsius on the lower x-axis, degrees Fahrenheit on the upper x-axis. There are two vertical axes. The one really want to draw your attention to is one on the right, which shows the maximum specific humidity. This is measured in grams of water per kilogram of air. So basically, how many parts per thousand in the atmosphere are water vapor. The red line defines the maximum possible specific humidity. And you can see that as we move from the left to the right of the diagram, this increases. So hot air is holding more moisture than cold air. The second thing that's very important here in the tropics is that the steepness of this line increases as we get to hotter temperatures. So there's a disproportionately large amount of moisture that can be held by disproportionately warmer temperatures. In Florida, we're quite accustomed to temperatures in the 90 Fahrenheit, 95 degree Fahrenheit range. This temperature is indicated on the top x-axis there at 95 degrees Fahrenheit in blue. At that level, you can see that the kilogram of air in Gainesville in the summertime can hold perhaps as much as 43 grams of moisture, water vapor, for every kilogram of air in the environment. Most of us can only live in Gainesville in the summertime because of air conditioners. What the air conditioner does is to draw in the air from outside at 95 degrees Fahrenheit and reduce the temperature to whatever you want it to be in the house or in your car. Perhaps in this case 77 degrees Fahrenheit. If you look at the left hand of the two blue lines, you'll see that it's marked as 77 degrees Fahrenheit, 25 degrees Celsius. You can see that I've cooled the air by 18 Fahrenheit or by 10 degrees Celsius. At 25 Celsius, 77 Fahrenheit, the maximum amount of moisture that a parcel of air can hold is 26 grams of moisture for every kilogram. The additional 17 grams, the difference between 43 and 26, has to be released to the atmosphere, and it does this by condensation, which we see as water droplets in the form of clouds, in the form of rain, or in Gainesville we can perhaps see it as drips coming out of one of those box air conditioners in the window, or dripping underneath your car when you stop in the summertime. If we were to take air at 68 degrees Fahrenheit, 20 degrees Celsius, then the maximum amount of moisture it can hold is only 19 grams per kilogram. This makes sense. The temperature is declining, the amount of moisture it can hold is declined. If for some reason we wanted to reduce the temperature of that air an additional 10 degrees Celsius, 18 degrees Fahrenheit, just as we did in the case of Gainesville, you can see that at 10 degrees Celsius, the maximum amount of moisture this air could hold is 11 grams per kilogram. This means that in reducing the temperature of this more temperate air from 68 degrees Fahrenheit to 50 degrees Fahrenheit, I have reduced the quantity of moisture in the air from 19 grams per kilogram to 11 grams per kilogram. This has released 8 grams of moisture for every kilogram of air, half as much as it did when I reduced the temperature 10 degrees Celsius at the higher temperatures. So in order to make condensation, clouds, and in order to get rain out of those clouds, we have to cool the atmosphere. And the most usual way to cool the atmosphere is to make it rise. Rising air is usually associated with clouds and precipitations as temperatures decline with altitude, as is shown in this graph here on the right hand side. On the horizontal axis are mean atmospheric temperatures in degrees Celsius, and on the vertical axis is some measure of altitude in the atmosphere going up in kilometers. The lower level of the atmosphere in which we live, and which is of most importance to the climate of Costa Rica, is called the troposphere, which extends up to about 10 kilometers above our heads in the tropics. You can see here that the temperatures are declining as we move from right to left along the horizontal axis, and that altitude is increasing as we go up the y-axis. So then if I make the air rise in the atmosphere, I move up the y-axis, then I'm driving down the temperatures and also the maximum moisture content that the air can hold along the x-axis. To understand the complexities of the climate of Costa Rica, we're going to take a look at the major seasonal breaks. And in the first break here, we're going to be looking at the season from November to April, which is variously known as verano, the summertime, even though it's a northern hemisphere winter here, or the dry season in much of Costa Rica. In this diagram, we've simplified the global climate zones. The zone in grey at 30 degrees north, roughly 30 degrees north, is a zone of high atmospheric pressure, which actually frequently sits off the coast of Florida over the Atlantic. At 0 degrees at the equator, we have a zone of low atmospheric pressure. We know from our initial discussions then that the wind intends to blow from 30 degrees north, the high pressure, to the low atmospheric pressure at the equator, as indicated by the grey dotted lines. Because these winds are blowing across the surface of the rotating globe in the northern hemisphere, they're deflected to the right of their intended paths. This gives rise to the heavy light mint colours with the black outlines. This is the direction, the dominant direction of winds at a global scale at these latitudes. We give the name to the wind, which is indicative of the region from which it came. In this case, the winds are coming from the northeast. These are the northeast trades, which dominate wind directions between 0 and 30 degrees north over the global system. The country of Costa Rica lies between about 8 degrees north and 11.5 degrees north. So you can see here it lies well within the belts of the northeast trades. So on a global scale, we can now see that the winds are coming off of the Caribbean and the tropical North Atlantic, blowing across the top of North and South America towards this narrow neck of land, the Central American Isthmus, which separates the Caribbean from the Pacific Ocean. The topography of Costa Rica lies at right angles to these trade winds. The trade wind direction here is indicated by the heavy blue arrow in the top right hand corner. The four major cordillera of Costa Rica are from the northwest down towards the southeast: Cordillera Guanacaste, Cordillera Tilarán, Cordillera Central, and Cordillera Talamanca. The winds are wanting to blow from the Caribbean side across the isthmus towards the Pacific, and then onwards towards their target, which is the low atmospheric pressure, generally located near the equator. As the winds blow onshore from the Caribbean over the Caribbean lowlands of Costa Rica, they meet the mountains and they were forced to rise. As they rise, we know that they're going into a cooler environment, therefore they must themselves cool and their ability to hold moisture decline. This produces condensation on the side of the mountains facing the wind, in which case we call it the windward side, and we're going to see clouds and rain in association with this region. By contrast, on the Pacific slope, indicated here by the wind directions of the orange arrow outlined in blue, the air is now passed over the Cordillera and is free to expand downwards back to lower elevations. At lower elevations, the air warms up. As the air warms up, it can hold more moisture, so there is no need for condensation, there's no clouds, and there's no rainfall. This side of the mountain, away from the winds, is called the leeward side and is generally dry. This figure here is a little complex. It's the result of a cross-section of meteorological stations across Costa Rica, stretching on the x-axis from the far left at the Pacific coast to the far right on the Caribbean coast. The shaded grey area indicates the elevation in meters of the topography at which, or the elevation at which the meteorological station is recorded. So you can see that the highest meteorological station here is close to 3,500 meters above sea level. That's about 3 to 3.5 kilometers. And you remember that the troposphere goes up to about 10 kilometers. So there's some substantial elevation here. The blue lines are indicated by are indicative of the average monthly rainfall at a particular station. The location of that station is shown by the longitude shown along the x-axis. So the very first blue dot on the right is a station which is on the Caribbean coast, right on the Caribbean coast. And reading off from the right hand vertical axis, you can see that it receives about 225 millimeters of precipitation in January. As we move inland and we start to see the interaction between those trade winds coming in off of the Caribbean, being forced to rise up over the topography, we see the rainfall increasing in January on average to perhaps 480 millimeters per month. As soon as we cross the divide, as soon as we cross onto the leeward side of the mountains, the left-hand side of the grey promontory there, you can see the rainfall drops to less than 200 millimeters a month, and for much of the Pacific slope there's virtually no precipitation whatsoever. So very clearly here we can see the role of the northeast trades interacting with the topography, forcing the air to rise, condensation and rainfall occurring on the Caribbean slope, and on the opposite side, on the Pacific slope, we have clear, dry, cloudless days. This map shows the results of plotting rainfall data from over 300 rainfall stations located throughout Costa Rica. The diagram on the left shows us the average monthly rainfall in millimeters that we'd expect to see in January, in the middle of that dry season. You can see on the left then the dominance of the red, which are rainfalls less than 100 millimeters on the Pacific slope, whereas on the Caribbean slope, to the right of Costa Rica there, if you like, as you look at it, you'll see greens and blues indicating 300, 400, even as much as 500 millimeters per month falling. How important is this season or this month in the overall rainfall? Well, we can look at the figure on the right, which shows us what percentage of the annual total rainfall this month represents. Once again, red colors indicate that this month is very low importance. It produces very little of the annual rainfall. And as we go through the rainbow up towards the blues and the purples, we find that this is a higher importance, that this month is contributing more. If rainfall was uniformly distributed throughout the 12 months, then we would expect to find that the rainfall color, the rainfall contribution, would be somewhere in there at about 8%, somewhere in the yellow color. So you can see that the Caribbean coast is getting about what you would expect if it was rainfall was uniformly distributed, whereas particularly the Pacific slope is getting a much lower percentage of precipitation than we'd expect if there was no strong seasonality. The next rain season is May to October, which is generally regarded as the rainy season, or invierno in Costa Rica. And here the rainfall generating mechanism we're going to be talking about is something called the Intertropical Convergence Zone, which for obvious reasons is shortened to the ITCZ. Again, we're going to revert to our very simple diagram of global weather patterns. We have our high atmospheric pressures at 30 degrees north and 30 degrees south, both of which are trying to send air towards the low atmospheric pressure located in and around the equator. In the northern hemisphere, those winds are deflected to the right of their intended path, giving rise to the northeast trades. In the southern hemisphere, they're deflected to the left of their intended path, giving rise to the southeast trades. You can see that my green and red arrows here, my two sets of trade winds, are converging on this zone at the equator. Now, the reason they're converging on this zone at the equator is indicated by the balloon, the hot air balloon, in the bottom right-hand corner. In general, this is a zone of the world which receives maximum energy from the sun, and so the air is hotter than most places around the world. We know with a warm hot air balloon that as soon as the flame is turned on, the air inside the balloon warms up, it expands, and the balloon goes upwards. Well, the same thing is happening on a global scale in terms of climate. The air rushing in from the northeast and southeast trades is warming up, and as it warms up, it rises in this giant circle around the globe, vertically moving away from the surface of the Earth. So what's lifting the air here and cooling it, and therefore potentially producing clouds and rainfall, is the excess heating associated with the sun and the maximum solar radiation. This is shown, as it were, in the third dimension in the little diagram to the left there of our global circulation. You can see my red arrow rising, and there's a green circulation to the north and a colorless circulation to the south. So in that equatorial type of zone, we've got warm air converging and rising at the intertropical convergence zone. This is the way that Costa Rica sits, generally speaking, with regard to the intertropical convergence zone in February, the dry season. Here we have our northeast trades, and because the overhead sun has migrated southwards towards the Tropic of Capricorn at 23.5 degrees south, as indicated by my little sunshine symbol in the bottom left-hand corner here of the diagram, that zone of converging air we would expect to have moved south of the equator. Now, in the case of the eastern equatorial Pacific, it doesn't move anywhere near as far south as we'd expect. And that's because of an extremely cold ocean current bringing lots of cold air water up from the Antarctic, shown by my blue arrow rising and spreading across in the equatorial region. This prevents my intertropical convergence zone from moving as far south in this region of the world as we might have expected. This diagram indicates the ITCZ by the orange hashed arrow, a hashed line, sitting at about 3 degrees north off the coast of Colombia. Now my southeast trades, you'll remember, are trying to reach this low atmospheric pressure indicated by the ITCZ at 3 degrees north in this particular region. So now my red arrows, which are my southeast trades, are coming up off the coast, off of Peru and this region just south of the equator. They are behaving like southeast trades. They're being deflected to the left of their intended path. As they cross the equator, trying to get to the low pressure at 30 degrees north, they become northern hemisphere winds and are subject to the laws of physics, and they are deflected to the right of their intended path. So now they do a flip in their direction. And so you can see that being brought back in towards this low atmospheric pressure at 3 degrees north, we've got moisture coming in off of the eastern equatorial Pacific, being forced to rise. As it rises, producing these large clouds and excessive rain along the intertropical convergence zone. But in February, that intertropical convergence zone is located at about 3 degrees south. During the northern hemisphere summer, the overhead sun appears to migrate northwards over the equator in March to be overhead of the northern part of Cuba on June 21st. This overhead sun slowly warms up the land and the oceans and drags that low pressure, that intertropical convergence zone, northwards with it as it heats up the land and the ocean. On average, the intertropical convergence zone in the eastern equatorial Pacific sits at about 10 degrees north in September. It gets this far north by about June, and it hovers here through from about June to October. Our invierno, our wet season, our rainy season, at least in much of Costa Rica. So now in this diagram you can see my orange line, my orange dashed line, has migrated northwards to 10 degrees, and that my winds coming across the equator, my cross equatorial westerlies, are now flowing directly into the southern part of Costa Rica, into Panama, and now I've got moisture being delivered by the northeast trades to one side of Costa Rica. I've got moisture being delivered to the other side by my cross equatorial westerlies, and also rainfall being generated by this warm rising air at the intertropical convergence zone. Here's a similar diagram to the one that you saw for January, except now these are for October. And you can see that indeed on the Caribbean side, we're still working with 200 to 300, if not 400 millimeters of precipitation on average in October. You'll recall that over on the left-hand side of the diagram, on the Pacific slope of my Cordilleras, I had rainfalls which were negligible in January. And now you can see that I've got between 300, 400, 500 millimeters of precipitation on a monthly basis here in the Central Valley of Costa Rica and along the Pacific coastal region. This left hand, if you like, increase in precipitation is partly the result of lifting over the topography of the south of the cross-equatorial westerlies, but more importantly, the lifting mechanism caused by the intertropical convergence zone, the excess heating causing the warm tropical air to rise. Here are two maps now for monthly precipitation totals in October, which is generally the height of the rainy season in much of Costa Rica. Now we see a very different pattern on the left hand side to the one which we saw in January. Now the deepest blues and purples are located on the Pacific slope of the isthmus. Here you can see the influence of my cross-equatorial westerlies bringing moisture in off the Pacific, and you can see the influence of my intertropical convergence zone somewhere in here at about 10 degrees. It's still not dry on the Caribbean side, but at least now you can see that there's still greens and yellows and blues, but it's drier than the Pacific slope. The figure on the right, remember, indicates how important this particular month is in delivering the total rainfall that you'd expect in a year. The deeper the blue, the higher the percentage of rainfall falling in that month, contributing to the annual total. So now you can see in all the way down the Pacific coast that we have about 20% of the annual rainfall, if not more, falling in a single month, in this case October. Remember that the yellow is what we'd expect if rainfall was uniformly distributed. You can see then the Caribbean has got pretty much what you'd expect if it was uniformly distributed, and the Caribbean coast itself, particularly in the south, is a little bit less than one might expect if it was uniformly distributed. A very significant feature interrupts this dominantly rainy season, particularly on the Pacific coast. And locally this is known as the Veranillo de San Juan, or commonly known, at least regionally, as the midsummer drought, or if you are up in Nicaragua, they call it the canicula. And this is a small break in that heavy rainfall which is usually experienced between May and November. It's called the Veranillo because, remember, they kind of got their seasons reversed. They call it the summer a northern hemisphere winter because for most places that's the dry warm time in Costa Rica. So this little summer of St. John indicates this little break where it becomes often drier than you would expect during the rainy season. In order to understand the Veranillo de San Juan and its origin, we have to understand something about a local feature which is called the Caribbean low-level jet, and how this Caribbean low-level jet interacts with the Central American Cordilleras. In this diagram, the Caribbean low-level jet is shown as the red arrow coming in towards Nicaragua and Costa Rica from the Caribbean. This is exactly the same position as the northeast trades, and in fact the Caribbean low-level jet, if you like, is embedded within those northeast trade winds. What is it that gives rise to jets of all types, in this case a low-level jet? Low level because it's low in the atmosphere. Well, one of the major causes is a thermal gradient, a steep gradient in the temperatures between two particular regions in the world. Now in July and August, the Veranillo de San Juan, the sun has migrated northwards towards the northern part of this diagram, towards northern Mexico and Cuba. Land warms up faster than the sea. So the sun has been overhead over northern South America longer than it has over the Caribbean, because the sun's moved up from the south. But also the landmass of northern South America has warmed up faster than the ocean of the Caribbean. So on this diagram you'll see I've got northern South America warms quickly, Caribbean warms slowly. So particularly in the early part of the summer, July, if you like, then there's this big contrast shown by the green to yellow arrow on the right, which shows a very steep thermal gradient. Along that gradient, frequently jet streams develop. That jet stream, as you can see, is pointing towards the zone between Costa Rica and Nicaragua. It's being funneled by the topography. There's a gap there. You can see the lake, you can see the lowlands there of Costa Rica. That wind is going to jet through that gap and burst out into the Pacific Ocean. So it's going to go from one ocean basin, the Atlantic, into another, the Pacific. Once it becomes free, once the wind becomes free of the topographic constraints, it's going to obey that rule that we talked about before, and is going to tend to be deflected towards the right of its intended path in the northern hemisphere. What this is going to do is it's going to blow the hot water off the surface of the Pacific back out into the Pacific Ocean, and it's going to allow cool water from deeper down in the ocean to rise. This figure here is from what's called the reanalysis. It's the run of some computer models of global climate based upon historic data. The arrows on the right indicate the direction and the strength of the winds that are blowing. So I've circled in red this zone that we talked about, which we're calling the Caribbean low-level jet. And the colours there are indicative of strengths. So not only is the length of the arrow indicator of the strength, but also the colour. So you can see these winds are blowing somewhere about 9 to 10 meters per second. That's 30 feet per second. This is really blowing very strongly. And you can see this concentration in the Caribbean basin pointing at northern Costa Rica, southern Nicaragua. What we're going to do is to take a pair of geologic scissors there at the top of the diagram, and we're going to snip open the atmosphere down a line which is equivalent to 80 degrees west of the equator, west of the prime meridian, excuse me. So you can see that would just touch the coast of southeast Florida, down through Cuba, down through Panama. But it would indicate to us what is being thrown, if you like, at Costa Rica. These are some fairly complicated diagrams. Each of the four squares represents one of the four seasons. We've got MAM to the top left, which is March, April, May. To the top right in red, because it's what we're really interested in, we've got JJA, June, July, August. Bottom left, September, October, November, SON. Bottom right, DJF, December, January, February. Along the horizontal axis of each diagram, we've got a measure of latitude. So we're going from 8 degrees north, 10, 12, 14, 16, up to 20 on the right hand side. So Costa Rica, the location of Costa Rica between about 8 degrees and 12 degrees is shown by the vertical dashed lines. And on the vertical axis, I've got a measure of atmospheric pressure in millimeters. Atmospheric pressure declines as you go away from the surface of the Earth. So we're going from 1,000 to 900, 800, 700, all right, 600. So we can consider this as being some way indicator of depth in the atmosphere. So height in the atmosphere on the vertical axis, north-south on the horizontal axis, and this is our slice at 80 degrees west. What is shown here, the numbers, the white numbers, are what are called anomalies of the westerly wind component. So by convention, we measure these as westerly wind components. So when I see a negative anomaly, -4, -6, it means that the wind is blowing less strongly in a west direction than one would normally expect by this number of meters per second. So whenever I see a negative number here, it means that the easterly wind has strengthened. It's less westerly, it's more easterly than normal. So what I want you to pay particular attention to is this sort of core of the Caribbean low-level jet that you can see as the purple circle in the top left-hand diagram for March, April, May. They're indicated as -8. Then over here on the right, the season that we're interested in, June, July, August, you can see this is now up to -10, -12 meters per second. So that's telling me that this low-level jet has intensified from 8 meters per second in an easterly direction to 12 meters per second. And then when we move into September, October, November, you can see that that identity of the jet has almost disappeared. It's now a big blob distributed throughout the troposphere, and the winds have dropped to about 6 meters per second. Picking up again a little in December, January and February to 8 to 10 meters. But what I want you to see is this intensification of the Caribbean low-level jet contemporaneous to the Veraneos de San Juan, particularly in July and August. In this diagram, you can see what happens when the Caribbean low-level jet, indicated to the right, coming in from the warm water of the Caribbean Ocean, is funneled between the highlands of the Cordilleras of Costa Rica and Nicaragua, rushes through the gap. As it rushes through the gap, that air blows across the surface of the Pacific, and it blows the warm water, indicated by the red rusty coloured water, back out into the Pacific Ocean. Colder water from deeper down in the Pacific is forced to rise up along particularly this northwest coast of Costa Rica. So cold water comes to the surface as the Caribbean low-level jet intensifies in July and August. Now, the warm waters off of the Pacific, you remember, are what are fueling the intertropical convergence zone, what are fueling our big rain-making machine. So what it does locally is it produces cooler water on the surface, something which is known as the Costa Rica Dome, all right, in the Gulf of Papagayo here. And the fishermen know all about it because this cold water has a lot of food for the fish in terms of plankton in it. From a climatological point of view, it drives our rain-making machine, our intertropical convergence zone, out into the Pacific, away from the coast of Costa Rica. Out of the top of those storms come cold, dry air which comes down. As this comes down over the Nicoya Peninsula and the Pacific coast of Costa Rica, we get very few clouds, we get a reduction in the quantity of precipitation. So here you can see the connection between the two major ocean basins. You can see the importance of the northeast trade winds. You can see this Caribbean low-level jet embedded in this moisture being driven in off the Caribbean, driving through this topographic gap, and then producing a local response over here in the other ocean basin, the Pacific. Can we see this pattern? Well, here again are the monthly rainfall distributions in Costa Rica, but now for the month of July, which we've taken as being representative perhaps of the Veraneos, even though the Veraneos generally occurs straddling both July and August and is of varying lengths of time from year to year. But I think it very clearly shows here the position of that Caribbean low-level jet and its intensification, with now the deep blues and the purples in the left-hand diagram showing 500, 600 millimeters of precipitation in a month here in those Caribbean lowlands as the wind jets in. And then on the other side over here in Nicoya, Guanacaste, in the valley of the Tempisque, you can see that we're now back down to perhaps 100 to 150 millimeters of precipitation. A tremendous contrast between what we saw in October, with now on one side of the Cordillera Tilarán and Cordillera Guanacaste, heavy precipitation, large precipitation totals, and on the other side, very low precipitation totals. On the right hand side, you can see then that this area of Guanacaste in particular is susceptible to the Veraneos de San Juan and up into the Central Valley. Now rainfall totals are dropping to, even though it's the rainy season, to about what we'd expect if rainfall was uniformly distributed through the year, or even slightly less than that. The final season that I want to draw your attention to reverts back to November to April, and very unusual rain generating phenomenon, which is fairly unique here to the Caribbean region of Central America. And the lifting mechanism here are cold fronts, and these are locally known as los nortes, the northern winds, giving an indication of which part of this continental system we're going to be looking for the origin of these. Here's our general global model. Unfortunately, it's got a little bit more complex now. So I want you to follow through here with me. So number one down here, this is for this period of November through April or March. Now we know that the overhead sun has migrated south of the equator. And so in most places in the world, we'd expect the intertropical convergence zone, this low pressure, to have moved south following the overhead sun. The high atmospheric pressure at 30 degrees north, number 2 on this diagram, has weakened quite considerably and moved a little bit south. So winds are still blowing out of the high towards the lows, and they got to obey the Coriolis effect. They got to deflect to their right in the northern hemisphere, to the left of their intended path in the southern hemisphere. Way up at 90 degrees north, there's high atmospheric pressure. Now there's usually high atmospheric pressure here because it's very cold air. This high atmospheric pressure intensifies during November to March. It intensifies during November to March because parts of the Arctic here are not going to see sunlight for many months. It'll be night for several months. So that means there's no supply of solar energy, and the air gets colder and colder and colder. So this high becomes very strong, it strengthens, and it expands southwards. Number 4 on this diagram represents a boundary between the Arctic air coming out from 90 degrees north and the subtropical air blowing out from 30 degrees high towards the north. Now this boundary line we sometimes call the planetary front. This boundary represents the balance between the strengths of the two high pressures, the Arctic high pressure and the 30 degree north high pressure. Now at this time of year, the Arctic high pressure is very much stronger than the 30 degree north high pressure, and so it pushes the subtropical air southwards. It restricts the northern movement. Here in Gainesville, we know that these are the times of the year when it can get very cold. We can even get frosts in Florida because of this cold air pushing out. North America is very unusual, at least in this context, in that its major mountain chains basically run north-south. So we have the Rockies and the complex associated with the Rockies to the west, and with the Appalachians to the east. And as you can see on this diagram, they make a giant funnel. That high altitude of those mountains protects the interior of the United States from the warming influence of either the Pacific or the Atlantic Oceans. So as my Arctic high gets really strong, the big H over Canada here, then it's able to push the cold air out down this funnel southwards. And it'll produce snow and freezing temperatures in Texas and Louisiana, which is virtually unheard of anywhere else in the world at those sorts of latitudes. That cold air comes pouring out over the Caribbean, down the coast of Mexico and Central America, sometimes as far south as Colombia. It comes in great surges of cold air passing over the Gulf of Mexico and the Caribbean. Cold air is more dense than warm tropical air. The molecules are more densely packed together because they don't have as much energy, and so this cold air coming down from Canada drives like a wedge under the warm tropical air which might have been sitting over the Gulf of Mexico and the Caribbean. So it mechanically forces that warm subtropical air to rise. Here's our lifting mechanism then along those fronts, just like we get here in Gainesville. We get a cold front, we often get rain. because the warm air is being forced to rise, temperatures of the warm air are declining, can't hold as much moisture, clouds, precipitation. So how does this fit into our picture for November through to April? Well, we know that we've got our northeast trade winds blowing strongly, bringing moisture from the warm Caribbean and the subtropical Atlantic. Our ITCZ out here, the orange diagram, orange dashed line is out of the picture. It's retreated southwards to about 3 degrees north, so it's not playing a part. But periodically we get this cold outburst indicated by the blue arrow with a green outline rushing down over the Caribbean and the Gulf of Mexico. Now this has to obey the same rules of physics as the other air masses. We know that it's intending to blow in this sort of southerly direction. It's in the northern hemisphere, and so it is wanting to be deflected or appear to be deflected to its right, as indicated by those little arrows, blue arrows coming out of the larger one. So they're wanting to blow inland. They're wanting to bring moisture and they want to bring it inland. It hits the coastline of Costa Rica and Nicaragua, and we know that there are mountains there. Now the cold air stays low, and so it basically gets dammed, if you like, by that cold, that barrier of Cordilleras. And so the impact of the Nortes is restricted very much to the coastal region of the Caribbean. Here we can see this influence in the rainfall figures for December. Again, on the left you can see red all the way down the Pacific coast of Costa Rica, perhaps just a little residual in the very extreme south here of the cross-equatorial westerlies and the ITCZ as it starts to migrate southwards and out of the country. But the feature I really want to draw your attention to are the high rainfalls now on the northern Caribbean coast of Costa Rica. So now we're getting rainfalls up here in the order of 500 to 600 millimeters. This is one of the few places in the tropics where there's actually a winter maximum of rainfall. Most places in the tropics have a summer maximum of rainfall. So here we can see this very unusual intrusion of cold air, much of it come all the way down from Canada, interacting with the subtropical and tropical air, and then being deflected towards the coast and producing this band of precipitation along the Caribbean coast. Hopefully you now understand a little better the complex global, regional and local factors which produce this highly complex pattern of annual precipitation totals that you see before you on this diagram. We also know that hidden within this single diagram is a set of information concerning seasonal variability. To show the depth of this information, let's take a couple of stations from opposing coastal regions of Costa Rica. To the right here is a graph displaying the mean monthly precipitation for Freeman on the Caribbean coast. Along the horizontal axis, numbered 1 to 12 of the 12 months of the year starting in January, and on the vertical axis we've got some measure of monthly precipitation. The tops and bottoms of the grey box represent the sort of ranges of monthly precipitation totals that we would expect 50% of the time. Within that we have a hashed line and a solid line. The hashed line is the average, the position of the average monthly precipitation, and the solid line is that of the median, the value of monthly rainfall that has exceeded 50% of the time. The tops and bottoms of the little whiskers indicate the very rare events, those which occur perhaps only 10% of the time. And the dots are the most rare of events. They indicate those events which occur maybe only 5% of the time. In looking at this diagram for Freeman, we can see two distinct peaks of rainfall. One peak corresponds to July, August. You can see that corresponds to the Veroneos on the Pacific coast. This is when the Caribbean low-level jet intensifies and we find that there's more rain coming on shore. The second is in November, December, January, and again this corresponds to the time when the trade winds and the Caribbean low-level jet intensify. By contrast, we can see that in August and September we have some of the lowest rainfalls. Now this is when we know that the Caribbean low-level jet weakens, as it does in March and April. Liberia is located in the far northwest part of the country in Costa. We know that this side of the mountain generally tends to operate in the reverse way, the inverse way to the rainfall pattern we see in Freeman. Whenever the trade winds and the Caribbean low-level jet are strong, this places Liberia on the rain shadow or the dry side of the mountain. So in those months of November, December through to April, when we know that the Caribbean low-level jet is strong and the trades are dominant, then we can see that in general there's virtually no rainfall in Liberia. In addition, we know that in these months of the year, the main rain generating mechanism in this particular zone, the intertropical convergence zone, is located far south at about 3 degrees north in the eastern equatorial Pacific. We see two peaks of rainfall here, the first in May and June, which is a little bit smaller than the second peak in September and October. We know these are associated with the migration of the intertropical convergence zone northwards and the cross-equatorial westerlies bringing moisture in from the Pacific coast. The Veroneos, during the time when the Caribbean low-level jet intensifies in August and September, is marked by this reduction of precipitation, which is common throughout the Pacific flank of the country. This map conveys information about the 3 consecutive months during which a particular rainfall station records on average the highest amount of rainfall. One part is the colours. The colours are fairly easily determined. They're telling us something about the percentage of the annual rainfall which falls in the wettest set 3 months. The greens, which are restricted very much to the Caribbean coast, indicate that there's a fairly uniform distribution even throughout the year. Even in the wettest 3 months, the rainfall received is only about 30%. If it was evenly distributed throughout the year, you would expect that to be 25%. So this is indicating that rain is falling fairly consistently throughout the year in this particular region. By contrast, the Pacific slope is highlighted by blues and going to dark blues or even purples. This is telling us that very high percentages, 50 to 60% of the annual precipitation, is falling in the 3 months indicated as being the wettest. What is harder here to determine is the letters associated with the map. In some places, the density of the recording stations is so great that it's hard to work out to determine individual letter codes. But the letter codes are telling us something about the 3-month sequence which contains the wettest times of year. So you may be able to see there on the extreme northwest coast value of JJA. That's telling us that the wettest 3 months are June, July and August. Over on the extreme northeast coast, the letter code is NDJ for November, December and January. So not only do we know how much rain in terms of the percentage of the annual total is falling in the wettest triad, we also can tell what that wettest triad is. Because of the different timing of the different rainfall generating processes operating in Costa Rica, we're going to see some marked differences in those particular timings. In the San Juan lowlands, the Caribbean lowlands in the north there, we can see there's a predominance of JJA, June, July and August. We know this is the time when the Caribbean low-level jet reaches its maximum, and this is arrowing in from the northeast over the Caribbean, bringing in moisture into this particular region. Along the coastal zone, you'll see a dominance of the letter code NDJ, November, December, January. This is this highly unusual tropical feature of a winter maximum of precipitation. This precipitation comes about because of the incursion of cold fronts and the fact that the Caribbean low-level jet, the trade winds, are also picking up at this time of the year. Most of the Pacific flank of Costa Rica displays the wettest times of the year as being ASO, August, September, October. We know that this is the time of year where we have the coincidence of the intertropical convergence zone reaching its maximum northern position and those cross-equatorial westerlies, while at the same time the opposing force, as it were, provided by the Caribbean low-level jet, as it is at its weakest. One final small feature is the appearance of September, October, November as being the wettest time of year in the extreme southern part of the country. This probably reflects the lingering effect of the cross-equatorial westerlies and the intertropical convergence zone as it moves southwards towards its winter position just north of the equator. This is the last part of the country which will experience that particular effect until the following year.